This is a NAND gate, a CMOS NAND gate. Specifically, there are 4 of them in there. It is a CD4011. And can I focus back on myself? Again. The NAND gate is kind of cool. The NAND gate and the NOR gate can be used to make any other logic gate that you want. If you want a 5-input XOR gate, you can build that out of NAND gates. If you want to go crazy and build a full working x86 microprocessor or CPU, you could build that out of NAND gates. Not that it would be a good idea to do that, but NAND gates mathematically and practically can be used to make any other logic gate, which makes them really kind of useful. And so I thought, if you can make anything out of a NAND gate, why can't you make an RF mixer out of a NAND gate? It would be a silly thing to do, but I did it. So join me for this video as I take you on a weird journey of mixing digital electronics with analog intentions. Let's go over to the bench and I'll walk you through what I've done. This abomination starts with an AND gate, so let's start there. Here's the logic symbol for an AND gate. NAND gate. It looks like an AND gate with a little circle in front of it, making it the opposite of an AND gate, and you see that reflected here in the truth table. It does the opposite of what an AND gate does. An AND gate is only 1 when the 2 inputs are 1, otherwise it's 0. This is only 0 when the 2 inputs are 1, otherwise it's 1. But what is a 1 and a 0? Typically, you might power a gate like this from something like 5 volts. So that might be 5 volts being 1, and 0 might be 0 volts. But that computers exist in the real world. CMOS chips are made up of field effect transistors and things like that. If you were to plot a graph of zeroness versus oneness against the voltage in, you'd hope it would be 0 here, and then at some threshold, it would magically turn into 1. But it doesn't work that way. There's a slope, and it's probably quite exaggerated here, but there's some threshold voltage around which it's a little bit 0 and a little bit 1. And that's what I'm abusing in this circuit. Here I've got 2 analog signals going into this NAND gate. I'll draw the actual circuit out here. They are capacitively coupled, so going in there like that. If you imagine this one was just held high for a second, like 5 volts, as a signal came between sort of this 0 and 1 level, the output would be operating between 1 and 0. You'd effectively have a high gain amplifier, because this slope here is actually really, really high. The point of digital chips is to have a very small region here between 0 and 1. We have a very high gain amplifier with negative slope, much like an op-amp. And the way that you tame an op-amp is you put a resistor in the feedback path, and that's what I've done here. And I've also got another one here, because these are both, it's almost like an op-amp with 2 negative inputs. Sorry, I'm off the screen. An op-amp with 2 negative inputs, so 2 negative feedback resistors, gives you this thing here where you end up modulating this output by these 2 inputs here. The good thing about putting these feedback resistors here is if there's no input signal here, this will sort of steady state around this V in, which means you can decouple the input and have a small signal in here to get a rather large swing on the output. And yeah, enough sort of theory and math and all that sort of stuff. Is there anything else I wanted to say theory and math wise? No, doesn't matter. Let's go into the circuit itself. Let's power it up and let's have a look, because I think it's pretty neat. That means I need to turn on the power supply. Sorry for the noise and the hum. While I'm waiting for that to power up, I'm using 10K resistors here and sort of about 50 nanofarads there. I've also got another, 82 nanofarads. I've just been picking these kind of randomly. I've been using the FA-FY method of choosing the appropriate values here, but let's call this 10K and sort of 50 nanofarads. And this is a CD4011 BCN, for what it's worth, is the NAND gate I'm using. There is my lovely schematic for people who ask for schematics. Let's turn it on. It's on. We get just a lot of noise here below 60 dB. The two inputs here are coming from the signal generators in my oscilloscope. Let's turn on the first signal generator. And we have a sine wave at 1 megahertz and an amplitude of 64 millivolts. If I change that amplitude, let's turn it up a bit. That's 250 millivolts. Anyway, let's look at the spectrum. Here is our 1 megahertz fundamental, and here are the harmonics. Because we're generating harmonics because we're in this region here, and at 250 odd millivolts, we're going to be distorting the signal, so you get all the harmonics generated. So let's turn that down and let's get a cleaner, fewer harmonics. I don't know if I'm blocking the screen. But here, whoop, I don't know, whatever, 50 odd millivolts. Great, we've got the signal, we've got some harmonics. Let's turn on a second signal. And my second one is at 1.4, let's take it up to 1.5 megahertz, and this is where the magic is happening. Here is my fundamental on channel A, my fundamental on channel B, and here is my first intermodulation product. The first intermodulation product is B minus A, or 1.5 minus 1, or 500 kilohertz. This is cool. If I change the frequency of that second one, you can see the first intermodulation product move up and down, which is cool. I can move the frequency of the first one, and it moves in the opposite direction. I don't know if I'm blocking, but that's cool because of the minus sign, or because they're getting closer in frequency. But yeah, so why is this cool? Why is this interesting? Intermodulation products are sort of the basis of sort of RF engineering, and this is where I have no idea what I'm talking about, but it's kind of cool. When you have these nonlinear products happening in a mixer, I haven't talked about what a mixer is, but yeah, look up another search to find that because I'm not the expert. But when you take nonlinear combinations of two signals, you get these intermodulation products. The first one of which is this signal, the frequency of it is the frequency of this signal minus the frequency of that signal. So we had like 1.5 megahertz minus 1 megahertz, and you get a frequency of 0.5 megahertz coming out. Why is that interesting? Well, let's say you're interested in tuning the radio to 101.7 FM. I don't know what that is. 106.7. That's PBS in Melbourne. You could tune a local oscillator to that frequency, and then you could tune your antenna to that frequency, and you put them into a mixer, and what you'll get out is the minute differences. Say it's a frequency modulated signal, you'll get these minute differences out, and those minute differences are in the audio frequency, and so you can decode FM radio. If you wanted to decode AM radio, you need intermodulation and things like that. It's a fundamental building block of radio electronics, and I don't know how I ended up in this rabbit hole, but I've now built my first circuit board on FR4 because that's what you do. There's no really good reason for it. I just thought, hey, why not look the part even if I don't know what I'm doing? It was a fun exercise. I've learned some stuff. I highly, highly doubt that this counts as a good RF mixer, given that I just got it working a few minutes ago and it's made from totally the wrong parts. But it does the job, and that's cool, and I wanted to share it with you. So hope you find it interesting. I'll see you in the next one. Bye.